Well, welcome back to our course, Computer Organization and Architecture. This lecture, we're going to be talking about internal memory. The next lecture, we'll be talking about external memory. And just to give a little bit of context, we're working through the second major section of this course, where we're talking about the computer system, and we're talking about the various ways in which memory is utilized. And so let's do an introductory review, if you will, of the things that we'll cover, and then we're going to come back to this at the end, and you'll see how this all comes together. So since we're talking about internal memory, we're going to be talking about how main memory is organized, and so we'll be thinking about it from various types of memory that exist, how it is organized, how it is created into chips, and we'll be thinking a couple other strategies there. So first of all, this is the semiconductor main memory. That's the sweet spot that has been used for quite some time. Second, we'll talk about error correcting. There's ways in which through various error correcting algorithms that you can double check if there is a failure in the actual memory storage that you can correct it. There's a topic called EDRAM, and so you'll understand what that means as we get through this lecture, and we'll be, as we've done several times, talk about the IBM perspective and the Intel perspective on how they do caching. And we did mention caching before. We'll get a lot more in depth and understanding about that. We'll talk about a type of DRAM, dynamic random access memory. And so DDR DRAM, and we'll talk about synchronous DRAM and then DDR SDRAM. So that will be an important type of memory that's used a lot. We'll talk about flash memory, its operation, and the two different ways that it's implemented, either using NOR or NAND. And so these are terms referred to as gates, and later lectures will talk about that. And then we'll also talk about some newer non-volatile solid-state memory techniques that are starting to be quite useful. So in earlier computers, the most common form of random access storage for computer main memory employed an array of donut-shaped ferromagnetic loops referred to as cores. And so this was before you had semiconductor memory. Hence, main memory was often referred to as a core, a term that persists to this day. The advent and advances of microelectronics has since vanquished the magnetic core memory. Today, the use of semiconductor chips for main memory is almost universal. Key aspects of this technology are explored in this section. The basic element of semiconductor memory is the memory cell. Although a variety of electronic technologies are used, all semiconductor memory cells share certain properties. They exhibit two stable or that semi-stable states, which can be used to represent binary 1 and 0. They're capable of being written into at least once to set the stage, and they're capable of being read to sense the state. So in figure 6.1 that we're showing, it depicts the operation of the memory cell. Most commonly, the cell has three functional terminals capable of carrying an electric signal. The select terminal, as the name suggests, selects a memory cell for a read or write operation. The control terminal indicates read or write. For writing, the other terminal provides an electrical signal that sets the state of the cell to 1 or 0. For reading, that terminal is used for output of the cell state. The details of the internal organization, functioning, and timing of the memory cells depends on the specific integrated circuit technology used and are beyond the scope of this book, this lecture, and what we're covering in this class, except we'll provide some brief summaries so you can understand that as we're going through this survey style type course. For our purposes, we will take it as given that individual cells can be selected for reading and writing operations. So here we're looking at the semiconductor memory types, and we'll get a chance to be looking at these one at a time. So maybe just becoming familiar with these terms as we're seeing it here. All the memory types that we will explore in this chapter are random access. That is, individual words of memory are directly accessed through wired-in addressing logic. Table 5.1 that we're showing here lists the major types of semiconductor memory. The most common is referred to as random access memory, or RAM. This is in fact a misuse of the term because of all the types listed in the table are random access. One distinguishing characteristics of memory that is designated as RAM is that it is possible both to read data from the memory and to write new data into the memory easily and rapidly. Both the reading and writing are accomplished through the use of electrical signals. The other distinguishing characteristics of RAM is that it is volatile. A RAM must be provided with constant power supply. If the power is interrupted, the data is lost. Thus, RAM can be used only as temporary storage. The two traditional forms of RAM used in computers are DRAM and SRAM, and newer forms of RAM are discussed in section 6.5, are non-volatile, and so those are all things that we're going to be covering in this lecture. So stay tuned where we're getting into more details. So first, let's talk about dynamic RAM, or dynamic random access memory. RAM technology is divided into two technologies, the dynamic and static. A dynamic RAM, DRAM, is made when cells that store data are charged on capacitors. The presence or absence of charge in a capacitor is interpreted as a binary 1 or 0. Because the capacitors have a natural tendency to discharge, dynamic RAMs require periodic charge refreshing to maintain the data stores. The term dynamic refers to the tendency of the stored charge to leak away even with power continuously applied. So we're not going to be getting too much into transistors and how things look at that level. Other forms of this course do that, but this is probably about as detailed as we're going to get. And so transistor in general, it can be done for amplifying. So say if you have a stereo or even a lot of your electronics that are with your TV or media center. But another form is it can be used for either on or off. And this on or off is really the major function that we're leveraging here. So figure 6.2a is a typical DRAM structure for an individual cell that stores 1 bit. The address line is activated when the bit value from this cell is to be read or written. The transistor acts as a switch that is closed, allowing current to flow if a voltage is applied to the address line, and open, no current flows if a voltage is present on the address line. So thus we're able to get either two binary levels, 1 or 0, from this device, the way it's operating. For the write operation, a voltage signal is applied to the bit line. A high voltage represents 1 and a low voltage represents 0. The signal is then applied to the address line, allowing a charge to be transferred to the capacitor. For the read operation, when the address line is selected, the transistor turns on and the charge stored on the capacitor is fed out onto a bit line and into a sense amplifier. The sense amplifier compares the capacitor voltage to a reference value and determines if the cell contains a logic 1 or a logic 0. The readout from the cell discharges the capacitor, which must be restored to complete the operation. Although the DRAM cell is used to store a single bit, or 0 or 1, it is essentially an analog device. The capacitor can store any charge value within a range. A threshold value determines whether the charge is interpreted as a 1 or 0. For figure 6.2b, so what we're showing on the right, we're showing what is typical for SRAM, a structure for an individual cell. You can see there's a lot more transistors here. T1, T2, T3, and T4 are ones we'll start out with, are cross-connected in arrangement that produces a stable logic state. In logic state 1, point C1 is high and point C2 is low. In this state, T1 and T4 are off and T2 and T3 are on. In logical state 0, point C1 is low and point C2 is high. In this state, T1 and T4 are on, and T2 and T3 are off. Both states are stable as long as the direct current, DC, voltage is applied. Unlike the DRAM, no refresh is needed to retain data. As in the DRAM, the SRAM address line is used to operate or close a switch. The address line controls two transistors, T5 and T6, that we see on the left and the right. When a signal is applied to this line, the two transistors are switched on, allowing for a read or write operation. For a write operation, the desired bit value is applied to line B, while its complement is applied to line B. The forces that this forces for the four transistors T1, T2, T3, and T4 into the proper state. For a read operation, the bit value is read from line B. So that's we get a chance to look at how things are done for DRAM and SRAM at the transistor level. Let's think a little bit more about SRAM. In contrast, a static SRAM or static random access memory is a digital device that uses the same logic elements used in the processor. In an SRAM, binary values are stored using traditional flip-flop logic configuration, which we'll talk about in chapter 12 for a description of flip-flops. A static RAM will hold its data as long as power is supplied to it. As in the DRAM case, the SRAM address line is used to open or close a switch. The address line controls two transistors, T5 and T6, which you saw on the last slide. When the signal is applied to this line, the two transistors are switched on, allowing a read or write operation. For a write operation, the desired bit value is applied to line B, while its complement is applied to line B. This forces the four transistors T1, T2, T3, and T4 into the proper state. For a read operation, the bit value is read from line B. So we talked about that as we were going through the last chart. So now let's do a comparison between SRAM and DRAM. Both static and dynamic RAM are volatile. That is, power must be continuously applied to the memory to preserve the bit values. A dynamic memory cell is simpler and smaller than a static memory cell. Thus, a DRAM is more dense. Smaller cells equals more cells per unit area and less expensive than a corresponding SRAM. On the other hand, a DRAM requires a supporting refresh circuitry. For larger memories, the fixed cost of the refresh circuit is more than compensated for by the smaller variable cost of DRAM cells. Thus, DRAM tends to be favored for large memory requirements. A final point is that SRAMs are somewhat faster than DRAMs because of these relative characteristics. SRAM is used for cache memory, both on and off chips, and DRAM is used for main memory. So now we're seeing the distinctions between these two different technologies and where they typically land in computer architectures. Well, let's talk about read-only memory, or ROM. As the name should suggest, a read-only memory contains a permanent pattern of data that cannot be changed. A ROM is non-volatile, that is, no power source is required to maintain the bit values in memory. While it is possible to read a ROM, random read-only memory, it is not possible to write new data into it. An important application of a ROM is microprogramming. This is something that is discussed in part 4 of this course, and so we'll be coming to that a little bit later. Other potential applications include library subroutines for frequently wanted functions, system programs, and function tables. For a modest size requirement, the advantage of ROM is that the data or program is permanently in main memory and need never be loaded from a secondary storage device. A ROM is created like any other integrated circuit chip, with the data actually wired into the chip as part of the fabrication process. This presents two problems. The data insertion step includes a relatively large fixed cost, whether 1 or 1,000 of copies of a particular ROM are fabricated. There's no room for error. If one bit is wrong, the whole batch of ROMs must be thrown out. And so it's you write only, and then you can read it as many times as you want. Another alternative is something called a programmable read only memory, or PROM. When a small number of ROMs with a particular memory content is needed, a less expensive alternative is the programmable ROM or PROM. Like the ROM, the PROM is non-volatile and may be written into only once. For the PROM, the writing process is performed electrically and may be performed by a supplier or customer at a time later than the original chip fabrication. Special equipment is required for the writing or, quote, programming process. PROMs provide flexibility and convenience. The ROM remains attractive for high volume production runs. Well, next, let's talk about three other type of what you could think of as read mostly memories: the EEPROM, the EEPROM, and the flash memory. Although variation on read-only memory is the read mostly memory, which is useful for applications in which read operations are far more frequent than write operations, but for which non-volatile storage is required. There are three commonly used forms: the EEPROM, the EEPROM, and the flash memory. The optically erasable programmable read-only memory, EEPROM, is read and written electrically as with PROM. However, before a write operation, all the storage cells must be erased to the same initial state by exposing of the package to an ultraviolet radiation source. Erasure is performed by shining an intense ultraviolet light through a window that is designed into the memory chip. This erasure process can be performed repeatedly. Each erasure can take as much as 20 minutes to perform. Thus, the EEPROM can be altered multiple times, and like the ROM and PROM, holds its data virtually indefinitely. For comparable amounts of storage, the EEPROM is more expensive than the PROM, but it has the advantage of multiple update capabilities. And so thus, say if you're trying to prototype something and you think you got the right program, but you're not sure, you can burn it, try it, and if it doesn't work, you can reprogram it. A more attractive form of read mostly memory is electrically erasable programmable read-only memory, EEPROM. This is a read mostly memory that can be written into at any time without erasing prior contents. Only the byte or bytes addressed are updated. The write operation takes considerably longer than the read operation, on the order of several hundred microseconds per byte. The EEPROM combines the advantage of non-volatility with the flexibility of being updatable in place using ordinary bus control, address, and data lines. EEPROM is more expensive than EEPROM and also is less dense, supporting fewer bits per chip. Another form of semiconductor memory is flash memory, so-called because of the speed with which it can be reprogrammed. It was first introduced in the mid-1980s. Flash memory is intermediate between EEPROM and EEPROM in both cost and functionality. Like EEPROM, flash memory uses an electrical erasing technology. An entire flash memory can be erased in 1 or a few seconds, which is much faster than EEPROM. In addition, it is possible to erase just blocks of memory rather than an entire chip. Flash memory gets its name originally because the microchip is organized so that a section of memory cells are erased in a single action, or a, quote, flash. However, flash memory does not provide byte level erasure. Like EEPROM, flash memory uses only one transistor per bit, and so achieves the high density, so it is comparable with EEPROM or EEPROM. Okay, well, let's look at a sample layout for a typical 16 megabit DRAM. And so we're showing an example here in figure 6.3. In this case, 4 bits are read or written at a time. Logically, the memory array is organized as 4 square arrays of 2048 by 2048 elements. Various physical arrangements are possible. In any case, the elements of the array are connected by both horizontal, that is row, and vertical columns lines. Each horizontal line connects to the select terminal of each cell in the row. Each vertical line connects to the data in and sense terminal, each cell in its column. Address line supply the address of the word to be selected. A total of log2 of W lines are needed. In our example, 11 address lines are needed to select 2048 rows. These 11 lines are fed into a row decoder, which has 11 lines of input and 2048 lines for output. The logic of the decoder activates a single one of the 2048 outputs depending on the bit pattern on the 11 input lines. Remember, 2 to the 11 is 2048. An additional 11 lines select one of 2048 columns of the 4 bits per column. 4 data lines are used for the input and output of 4 bits to and from a data buffer. On input, which is right, the bit driver of each line is activated for a 1 or a 0 according to the value of the corresponding data line. On output, that is read, the value of each line is passed through a sense amplifier and presented to the data lines. The row line selects which row of cells is used for reading or writing. Because only 4 bits are read or read or written to the DRAM, there must be multiple DRAMs connected to the memory controller to read or write a word of data to the bus. Note that there are only 11 address lines, A0 through A10, half of the number you would expect for a 2048 by 2048 array. This is done to save on the number of pins. The 22 required address lines are passed through a select logic external to the chip and multiplex onto the 11 address lines. First, 11 address lines are passed to the chip to define the row address of the array, and then another 11 address lines are presented for the column address. So we're trying to limit the number of pins, and we'll see that in the next slide, how that would be a helpful thing. As an aside, multiplex addressing plus the use of square arrays result in a quadrupling of the memory size with each new generation of memory chips. One more pin devoted to addressing doubles the number of rows and columns, and so the size of the memory chip grows by a factor of 4. The figure that we're showing here, figure 6.3, also indicates the inclusion of a refresh circuit. So this we're seeing as another thing that's necessary for DRAM. All DRAM requires a refresh operation. A simple technique for refreshing, in effect, is to disable the DRAM chip while all data cells are refreshed. The refresh counter steps through all of the rows values for each row. The output lines from the refresh counter are supplied to the row decoder, and the RAS line is activated. The data are read out and written back into the same location. This causes each cell in the row to be refreshed. So you're basically recharging the capacitors associated with each cell. Now we're looking at the typical memory package pins and signals for a couple of memory devices. So as mentioned in chapter 2, an integrated circuit is mounted on a package that contains pins for connecting into the outside world. And so there's a chip inside of this package. So first of all, for figure 6.4a, it shows an example of an EEPROM package, which is an 8 megabit chip organized as a 1 megabit times 8. In this case, the organization is treated as a 1 word per chip package. The package includes 32 pins, and so we have to figure out how to allocate that, which is one of the standard chip package sizes. The pins support the following signals. The address of the word being accessed for a 1 megabit words are a total of 20, so 2 to the 20 is 1 megabit. Pins are needed, so you need A0 through A19. The data lines to be read out consist of 8 lines, D0 through D7. The power supply to the chip is VCC, and the ground is labeled as VSS. A chip enable CE pin, because there are more than one memory chips, each of which is connected to the address line, the CE pin is used to indicate whether or not the address is valid for this chip. The CE pin is activated by logic connected to the higher order bits of the address lines. So for example, address bits above A19, the use of the signal is illustrated presently. So keep that in mind. We'll show some block diagrams. A program voltage VPP that is supplied during programming write operations. A typical DRAM pin configuration is also shown in 6.4b for a 16 megabit chip organized as a 4 megabit times 4. There are several differences from a ROM chip. Because a RAM can be updated, the data pins are input and output. The write enable WE and output enable OE pins indicate whether this is a write or a read operation. Because the DRAM is accessed by row and column, and the addresses multiplex, only 11 address pins are needed to specify the 4 megabit row / column combination. 2 to the 11 times 2 to the 11 is 2 to the 22, which gives us 4 megabit. The function of the row address select, the RAS, and column address select CAS pins were discussed previously. Finally, the NC, the no connect pin, is provided, so there are an even number of pins, and we're staying with the configuration for this standard 24 bit 24 line package. Okay, now we're looking at an example of a 256 kilobyte memory organization. If a RAM chip contains only 1 bit per word, then clearly we need at least a number of chips equal to the number of bits per word. So for an example, in this figure 6.5, it shows how a memory module consisting of 256K 8-bit words could be organized. For 256K words, an 18-bit address is needed and is supplied to the module from some external source, i.e. the address lines of a bus to which the module is attached. The address is presented to 8 individual 256K times 1-bit chips, each of which provides the input and output of 1 bit. So now let's look at a 1 megabit memory organization. So this organization works as long as the size of the memory equals the number of bits per chip. In this case, in which larger memory is required, an array of chips is needed. So now in the figure 6.6, it shows the possible organization of a memory consisting of 1 megabit words by 8 bits per word. In this case, we have 4 columns of chips, each column containing 256K words arranged as in figure 6.5. In the last figure, the last slide we showed, for 1 megabit words, 20 address lines are needed. The 18 least significant bits are routed to all 32 modules. The high order 2 bits are input to a group select logic module that sends a chip enable signal to one of the 4 columns of modules. Okay, well, let's talk about interleaved memory. This is another possibility that can be used. And so the memory is composed of a collection of DRAM memory chips. A number of chips can be grouped together to form a memory bank. It is possible to organize the memory banks into a way known as interleaved memory. Each bank is independently able to service a memory read or write requests, so that a system with K banks can service K requests simultaneously, increasing memory read and read or write rates by a factor of K. If consecutive words of memory are stored in different banks, then the transfer of the block of the memory is sped up. You can go ahead and look in Appendix C of the textbook, and it explores the topic of interleaved memory in more detail, but we just wanted to at least give you a sense of that. Well, the next section that we wanted to talk about was error correction. And so let's introduce it here, and we'll get more specifics about a couple different ways it can be done. A semiconductor memory system is subject to errors. These can be categorized as hard failures, so hardware failures, maybe you can think about it, and soft errors. A hard failure is a permanent physical defect so that the memory cell or cells affected cannot reliably store data but become stuck at 0 or 1, or switch erratically between 0 and 1. Hard errors can be caused by harsh environment abuse, manufacturing defects, and wear. A soft error is a random, non-destructive event that alters the contents of one or more memory cells without damaging the memory. Soft errors can be caused by power supply problems or alpha particles. These particles result from radioactive decay and are distressingly common because radioactive nuclei are found in small quantities in nearly all materials. Both hard and soft errors are clearly undesirable, and most modern main memory systems include logic for both detecting and correcting the errors. So we have to handle both of those. Find out if there's an error, and if there is, figure out how we're going to deal with it. So here we're getting a general sense of an error correcting code function. So this figure illustrates in general terms how this process is carried out. When data are to be written into memory, a calculation depicted as a function f is performed on the data to produce a code. Both the code and the data are stored. Thus, if an m-bit word of data is to be stored and the code is of length k bits, then the actual size of the stored word is m plus k bits. And so there's k bits used for error detection and correction. When the previously stored word is read out, the code is used to detect and possibly correct errors. A new set of k code bits is generated from the k data bits and compared with the fetch code bits. The comparison yields one of 3 results. So first is no errors are detected, the fetch data bits are sent out. Second, an error is detected and it is possible to correct the error. The data bits plus error correction bits are fed into a corrector, which produces a corrected set of m bits to be sent out. And third, an error is detected, but it's not possible to correct it. The condition is reported. Codes that operate in this fashion are referred to as error correcting codes. A code is characterized by the number of bit errors in a word that it can correct and detect. So let's look at an example here. First of all, we'll talk about Hamming error code, correcting code. The simplest of the error correcting codes is a Hamming code devised by Richard Hamming at Bell Laboratories. Figure 6.8, as we're showing here, uses a Venn diagram to illustrate the use of this code on a 4 words m equals 4. With 3 intersecting circles, there are several compartments. We assign the 4 data bits to the inner compartment. That's figure 6.8a. The remaining compartments are called parity bits. Each parity bit is chosen so that the total number of ones in its circle is even. So figure 6.8b. Thus, because circle A includes 3 data ones, the parity bit in that circle is set to 1. Now, if an error changes one of the data bits, and so now we're looking at figure 6.8c, it is easily found. By checking the parity bit discrepancies are found in circle A and circle C, but not in circle B. Only one of the 7 compartments is in A and C, but not B. The error can therefore be corrected by changing that bit. So that's the process of a Hamming code with a single bit correction. So here we're showing the increase in word length with error correcting. And so the first 3 columns of table 6.2 on this slide lists the number of check bits required for various data word lengths. For convenience, we would like to generate a 4-bit syndrome for an 8-bit data word with the following characteristics. If the syndrome contains all zeros, no error has been detected. If the syndrome contains 1 and only 1 bit set to 1, then an error has occurred in one of the 4 check bits, no correction is needed. If the syndrome contains more than one bit set to 1, then the numerical value of the syndrome indicates the position of the data bit in error. This data bit is inverted for correction. So this gives you an idea of how you can be doing correction. Here we're looking at the layout of data bits and check bits. And so to achieve these characteristics, the data and check bits are arranged into 12-bit words as depicted in the figure we're showing, 6.9. The bit position are numbered from 1 to 12. Those bit positions whose position numbers are powers of 2 are designated as check bits. So that's where we're getting some insight into how we can be looking at having data and correction on top of that. So now let's look at the check bit calculation. So we'll just try and give an example. So this here we're trying to show the illustration of the calculations. The data and check bits are positioned properly in the 12-bit word. 4 of the data bits have a value 1 shaded in the table, and their bit positions values are exclusive OR to produce the Hamming code 0111, which forms the 4 check digits. The entire block that is stored is 001101001111. Suppose now that data bit 3 in position 6 sustains an error and is changed from 0 to 1. The resulting block is 001101101111 with a Hamming code of 0111. An exclusive OR of the Hamming code and all the bit position values for non-zero data bits results in a 0110. The non-zero result detects an error and indicates that the error is in position 6. So thus we were able to find it and we're able to have a algorithm for correcting it. Here we're having something that's called a Hamming SecDec code. The code described is known as a single error correcting sec code. More commonly, semiconductor memory is equipped with a single error correcting, double error detecting SecDed code. And as the table 6.2 shows, such code requires 1 additional bit compared with the sec code. Okay, I believe I just found an error on that chart, so I corrected it. So it's a SecDed code. So sorry for that, but I'm trying to make that change real time here. So figure 6.11 illustrates how such a code works. Again, with a 4-bit data word, the sequence shows that if 2 errors occur, not 1 but 2, figure 6.11c, the check produce procedure goes astray and worsens the problem by creating a 3rd error, E. To overcome the problem, an 8th bit is added that is set so that the total of 1s in the diagram is even. The extra parity bit catches the error F. So I'm going to read that again. So the sequence shown in that if 2 error occurs, figure 6.11c, so we're seeing that over here. The check procedure goes astray in D, so we're seeing that, and worsens the problem by creating a 3rd error in what we're seeing in E. To overcome this problem, an 8th bit is added that is set so the total number of 1s in the diagram is even. The extra parity bit catches the error F. An error correcting code enhances the reliability of memory at the cost of adding complexity. With a 1 bit per chip organization, a SecDed code is generally considered adequate. So first, for a IBM, an IBM 30, 30 something something implementation uses a 8-bit SecDed code for each 64 bits of data in main memory. Thus, the size of main memory is actually about 12% larger than the what's apparent to the user. The VAX computer uses a 7-bit SecDed for each 32 bits of memory for a 22% overhead. A number of contemporary DRAMs use 9 check bits for each 128 bits of data for a 7% overhead. So it can range 7 to 22%. So maybe just ballparking on the order of 10% is something that modern systems tend to use. So what about advanced DRAM organization? Now we're going to be getting into some of these more descriptive things that if you were to actually go buy memory, you're going to see some of these terms. So as discussed in chapter 1, one of the most critical system bottlenecks when using high performance processors is the interface to main internal memory. The interface is the most important pathway in the entire computer system. The basic building block of main memory remains the DRAM chip as it has for decades. Until recently, there has been no significant changes in DRAM architecture since the 1970s. The traditional DRAM chip is constrained both by its internal architecture and its interface to the processor's memory bus. We have seen that one attack on the performance problem of DRAM main memory has been to insert one or more levels of high-speed SRAM cache between the DRAM main memory and the processor. But SRAM is much costlier than DRAM, and expanding cache size beyond a certain point yields diminishing returns. So that's one option. In recent years, a number of enhancements into the basic DRAM architecture have been explored. The schemes that are currently dominate the market are SDRAM and DDR DRAM. And we're going to turn to these next and discuss those. So hold on and you'll get a chance to know what that means. So first, talk about SDRAM or synchronous DRAM. One of the most widely used forms of DRAM is the synchronous DRAM. Unlike the traditional DRAM, which is asynchronous, the SDRAM exchanges data with a processor synchronized to an external clock signal and running at the full speed of the processor or memory bus without imposing wait states. In a typical DRAM, the processor presents addresses and control levels to the memory, indicating that a set of data at a particular location in memory should be either read from or written into the DRAM. After a delay, the access time that the DRAM either writes or reads the data. During the access time delay, the DRAM performs various internal functions such as activating the high capacitance of the row and column lines, sensing the data, and routing the data out through the output buffers. The processor must simply wait through this delay, slowing system performance. With synchronous access, the DRAM moves data in and out under control of the system clock. The processor of other master issues the instruction and address information, which is latched by the DRAM. The DRAM then responds after a set number of clock cycles. Meanwhile, the master can safely do other tasks while the SDRAM is processing the request. So a lot of more sophistication is being introduced as we start to be thinking through these things, as I hope you're getting a sense of that as we're going through this survey of memory, internal memory for this particular lecture. So in figure 612, we're showing the internal logic of a typical 256 megabit SDRAM, typical of SDRAM organizations. And so you can pause the video if you like and get a chance to be looking at this a little bit more closely. But this is the things in a diagram, what we just described in the last chart. Here in table 6.3, we define the various pin assignments. The SDRAM employs a burst mode to eliminate the address setup time and row and column lines. Pre-charge time after the first access. In burst mode, a series of data bits can be clocked out rapidly after the first bit has been accessed. This mode is used when all the bits to be accessed are in sequence in the same row of the array as the initial access. In addition, the SDRAM has a multiple bank internal architecture that improves opportunities for on-chip parallelism. So earlier we talked about some of the studies that have showed that typically memory tends to couple what you have in terms of memory calls. And so here we're seeing an architecture that is allowing to help along that line. The mode register and associative control logic is another key feature differentiating SDRAM from conventional DRAM. It provides a mechanism to customize the SDRAM to suit specific system needs. The mode register specifies the burst length, which is the number of separate units of data synchronously fed onto the bus. The register also allows the programmer to adjust the latency between receipt of a read request and beginning of a data transfer. The SDRAM performs best when it is transferring large blocks of data serially, such as the applications like word processing, spreadsheets, and multimedia. So now in this figure, it shows an example SDRAM operation using a timing diagram. So we're going to be thinking about some of the stuff that we just mentioned. And so a timing diagram shows a signal level at a line as a function of time. By convention, the binary 1 signal level is depicted as a higher level than that of a binary 0. Usually binary 0 is the default value. That is, if no data or other signal is being transmitted, then the level on that line is represented by binary 0. A signal transitioning from 0 to 1 is frequently referred to as the signal's leading edge, and transition from 1 to 0 is referred to a trailing edge. Such transitions are not instantaneous, but this transition time is usually small compared with the duration of a signal level. For clarity, the transition is usually depicted as an angled line that exaggerates the relative time from the transition takes. And so we're seeing this here. This is where you have those transitions going on. Signals are sometimes represented in groups shown as shaded areas in figure 613. For example, if data are transferred a byte at a time, then 8 lines are required. Generally, it is not important to know the exact value being transferred on such a group, but rather whether signals are present or not. For SDRAM operation in figure 613, the burst length is 4 and the latency is 2. The burst read command is initiated by having CS and CAS low while holding RAS and WE high on the rising edge of the clock. The address input determines the starting column address for the burst, and the mode register sets the type of burst, sequential or interleaving. And the burst length, 1, 2, 4, 8, or full page, the delay from the start of the command to when the data from the first cell appears on the output is equal to the value of the CAS latency that is set in the mode register. Well, here's another example of a performance improvement that has really taken place in a nice way. So we're talking about double data rate. That's what the DDR stands for. So DDR SDRAM. So we've already talked about the SDRAM and before that DRAM. And so now we're adding yet another layer that's helping for performance improvement. Although SDRAM is a significant improvement on asynchronous RAM, it still has shortcomings that unnecessarily limit the I/O data rate that can be achieved. To address these shortcomings, a new version of SDRAM, referred to as double data rate DRAM or DDR RAM, provides several features that dramatically increases the data rate. DDR DRAM was developed by the JEDEC Solid State Technology Association, the Electronic Industries Alliance Semiconductor Engineering Standardization Body. Numerous companies make DDR chips, which are widely used in desktop computers and servers. DDR achieves higher data rates in three ways. First, the data transfer is synchronized to both the rising and falling edge of the clock, rather than just the rising edge. So that's number one. This doubles the data rate, hence the term double data rate. Second, DDR uses higher clock rates on the bus to increase the transfer rate. And third, a buffer scheme is used as explained subsequently. So here we see some more details of the DDR characteristics. So JEDEC has thus far defined 4 generations of DDR technology, as we're showing here in table 6.4. The initial DDR version makes sense. The initial DDR version makes use of a 2-bit prefetch buffer. The prefetch buffer is a memory cache located on the SDRAM chip. It enables the SDRAM chip to pre-position bits to be placed on the data bus as rapidly as possible. The DDR I/O bus uses the same clock rate as a memory chip, but because it handles 2 bits per cycle, it achieves a data rate that is double the clock rate. The 2-bit prefetch buffer enables the SDRAM chip to keep up with the I/O. And so here we're seeing a little bit of information here, and also the description of DDR1, DDR2, DDR3, DDR4. And so that's the first thing that you might see. And so if you are a computer geek and you've made your own, you might want to be figuring out what you have, DDR1, 2, 3, or 4. So to understand the operation of the prefetch buffer, we need to look at it from the point of view of a word transfer. The prefetch buffer size determines how many words of data are fetched across multiple DDR chips every time a column command is performed with DDR memories. And so in this chart, as we're having this discussion, we're looking at the DDR generations, and you can see how these have gotten more complicated over time: SDRAM, DDR, DDR2, DDR3, and DDR4. Because the core of the DDRAM is much slower than the interface, the difference is bridged by accessing information in parallel and then serializing it out the interface through a multiplexer, or also called a MUX. Thus, DDR prefetches 2 words, which means that every time a read or write operation is performed, it is performed on 2 words of data and burst out of or into the SDRAM over 1 clock cycle on both clock edges for a total of 2 consecutive operations. As a result, the DDR I/O interface is twice as fast as the SDRAM core. Although each new generation of SDRAM results in much greater capacity, the core speed of the SDRAM has not changed significantly from generation to generation. To achieve greater data rates than those afforded by the rather modest increase in SDRAM clock rates, JEDEC increased the buffer size. For DDR2, a 4-bit buffer is used, allow allowing for words to be transferred in parallel, increasing the effective data rates by a factor of 4. For DDR3, an 8-bit buffer is used and a factor of 8 speedup is achieved. And then the downside is the prefetch. It is effectively determines the minimum burst length for the SDRAM. For example, it is very difficult to have an efficient burst length of 4 words with DDR3 prefetch of 8 words. Accordingly, the JEDEC designers chose not to increase the buffer size to 16 bits for DDR4, but rather to introduce the concept of a bank group. Bank groups are separate entities such that they allow a column cycle to complete within a bank group, but that column cycle does not impact what is happening in other bank groups. Thus, the true prefetch of 8 can be operated in parallel in the 2 bank groups. This arrangement keeps the prefetch buffer size the same as DDR3 while increasing performance as if the prefetch is larger. So in this figure, it shows a configuration with up to 2 bank groups with DDR4, up to 4 bank groups can be used. Okay, next we'll talk about embedded DRAM, EDRAM. And so an increasing widespread technology used in the memory hierarchy is the embedded DRAM or EDRAM. EDRAM is a DRAM integrated on the same chip or MCM as an application-specific integrated circuit or ASIC or microprocessor. For a number of metrics, DRAM is intermediate between on-chip SRAM and off-chip DRAM. For the same surface area, DRAM provides a larger size memory than SRAM, but smaller than off-chip DRAM. EDRAM's cost per bits is higher when compared to equivalent standalone DRAM chips used as external memory, but it has a slower cost per bit than SRAM. Access times in EDRAM is greater than SRAM, but because of its proximity and the ability to use wider buses, EDRAM provides faster access than DRAM. A variety of technologies are used in fabricating EDRAM, but functionally they use the same designs and architectures as DRAM. So the reference that's listed in the text lists the following as the trends that have led to increasing use of EDRAM. And so we have a variety of good references that you can see that how these things that may at times not be intuitive, why they're actually used. And for larger systems and high-end applications, the spatially located curves have become flatter and wider, meaning that the likely area of memory for upcoming references is larger. This makes DRAM-based caches attractive due to their bit density. On-chip or MCM DRAM matches the performance of off-chip SRAM so that greater cache size can be achieved by replacing some on-chip areas that would otherwise be dedicated to SRAM with DRAM, avoiding or reducing the need for off-chip SRAM or DRAM. EDRAM generally dissipates less power than SRAM. So now we're seeing that once again the development of different type of technologies, and so how it eventually over time affects the architecture and slowly moving in one direction or another. Well, let's look at things for the IBM case. For an IBM Z13 system uses the EDRAM at 2 levels of the cache hierarchy, as we're showing. This is something that's you can go back to figure 410 as well to give you more context for what we're talking about here with the IBM Z13. Each processing unit PU chip with up to 8 cores has a shared 64 megabit EDRAM L3 cache. This is an example of an EDRAM integrated on the same chip as the microprocessors. 3 PU chips share a 4 megabit EDRAM L4 cache. And so you go back to figure 518 to see an example of what that would look like. The L4 cache is on a separate storage controller SC chip. This is an example of an EDRAM integrated on the same chip with other memory related logic. The L4 cache on each SC chip has 480 megabit of non-inclusive cache and 224 megabit non-data inclusive coherent or NIC directory. The NIC directory consists of tags that point to the L3 owned lines that have not been included in L4 cache. Figure 615 also shows the physical layout of the SC chip. About 60% of the surface area of the SC chip is devoted to the L4 cache and the NIC directory. The remainder of the chip includes L4 cache, controller logic, and IO logic. Now let's think about things for the Intel Core systems. Intel has shipped a number of products with an eDRAM position as an L4 cache. Figure 616A shows this arrangement. The eDRAM is accessed by a store of L4 tags contained within the L3 cache of each core, and as a result acts more as a victim cache to the L3 rather than a DRAM implementation. Any instruction or hardware that requires data from the eDRAM has to go through the L3 and do the L4 tag conversion, limiting its potential. In more recent products, the Intel removed the eDRAM from the position as an L4 cache, as shown in figure 616B. This removed an undesired dependency between the capacity of the eDRAM and the number of cores. In this new arrangement, the eDRAM is effectively no longer a true L4 cache, but rather a memory side cache. This has a number of benefits such that each and every memory access that goes through the memory controller gets looked at by the eDRAM. On a satisfied hit, the value is obtained from there. On a miss, a value gets allocated and stored in the eDRAM. Thus, rather than acting as a pseudo L4 cache, the eDRAM becomes a DRAM buffer and automatically transparent to any software, whether it's a CPU or an IGP, that requires DRAM access. As a result, other hardware that communicates through the system agent, such as PCI devices or data from the chipset, and requires information in DRAM, does not need to navigate through the L3 cache on the processor. Next, let's talk about flash memory. We've briefly introduced this, and now we get a chance to be looking at it a little bit more in detail. Another form of semiconductor memory is flash memory. Flash memory is used both for internal memory and external memory applications. Here we provide a technical overview and look at its use for internal memory. For the next chapter, the next lecture, we'll go over its external memory applications. It was first introduced in the mid-1980s. Flash memory is intermediate between EEPROM and EEPROM in both cost and functionality. The EEPROM flash memory uses an electrical erasing technology. An entire flash memory can be erased in 1 or a few seconds, which is much faster than EEPROM. In addition, it is possible to erase just blocks of memory rather than an entire chip. Flash memory gets its name because the microchip is organized so that a section of the memory cell are erased in a single action or flash. However, flash memory does not provide byte-level erasure. Like EEPROM, flash memory uses only one transistor per bit, and so achieves the high density as compared with EEPROM of EEPROM. So here in this figure, we're looking at flash memory operation, and it shows the basic operations that take place. So figure 617A depicts the operation of a transistor. The transistor exploits the properties of semiconductors so that a small voltage applied to the gate can be used to control the flow of a large current between the source and the drain. In a flash memory cell, a second gate called a floating gate, because of its insulated by a thin oxide layer, is added to the transistor. Initially, the floating gate does not interfere with the operation of the transistor. So we're seeing that in figure 617b. In this state, the cell is deemed to represent binary 1. Applying a large voltage across the oxide layer causes electrons to tunnel through it and become trapped on the floating gate, where they remain even if the power is disconnected. So we see that in figure 617c. In this state, the cell is deemed to represent binary 0. The state of the cell can be read by using external circuitry to test whether the transistor is working or not. Applying a large voltage in the opposite direction removes the electrons from the floating gate, returning it to a state of binary 1. An important characteristic of flash memory is that it's persistent memory, which means that it is retained data when there is no power applied to the memory. Thus, it is useful for a secondary, that is external storage, and as an alternative to random access memory in computers. We'll get into some more of those applications in the next lecture, in the next chapter. So let's look at the flash memory structure. There are two distinctive types of flash memories designated as NOR and NAND. We're seeing this in this figure 618. In NOR flash memory, the basic unit of access is a bit, referred to as a memory cell. Cells in NOR flash are connected in parallel, so the bit lines, so that each cell can be read. You can read, write, or erased individually. If any memory cell of the device is turned on by the corresponding word line, the bit line goes low. This is similar in function to a NOR logic gate. So NOR is one of the digital logic things that we'll be talking about later in the course, if that isn't familiar to you at this moment. Then we have the NAND flash memory. It is organized in transistor arrays with 16 or 32 transistors in series. The word line goes low only if all the transistors in the corresponding word line are turned on. This is similar in function to a NAND logic gate, and we'll be coming back to that shortly. So here we have Kvyat graphs, or another word I'm familiar with is spider charts for flash memory. Although the specific quantitative values of various characteristics of NOR or NAND are changing year by year, the relative difference between the two types has remained stable. These differences are usefully illustrated by the graph shown here in 619. NOR flash memory provides high-speed random access. It can read and write data to specific locations and can reference and retrieve a single byte. NAND reads and writes in small blocks. NAND provides higher bit density than NOR's and greater write speeds. NAND flash does not provide a random access external address, but an address bus, so that the data must be read on a blockwise basis, also known as page access, where each block holds hundreds to thousands of bits. For internal memory in an embedded system, NOR flash memories has traditionally been preferred. NAND memories has been making some inroads, but NOR remains dominant technology for internal memory. It is ideally suited for microcontrollers, where the amount of program code is relatively small and a certain amount of application data does not vary. For example, the flash memory in figure 1.16 is NOR memory. So you can go back to chapter 1 to review that figure if you'd like. NAND memory is better suited for external memory, such as USB flash drives, memory cards, and digital cameras, MP3 players, and things like that, in what are known as solid-state disk, SSD, and we're going to be talking about that in the next chapter, in chapter 7. So the traditional memory hierarchy has consisted of 3 levels. And so we have static RAM or SRAM. SRAM provides rapid access time, but is the most expensive and the least dense, that is bit density. SRAM is suitable for cache memory. We've talked about cache memory. Next, we have dynamic RAM or DRAM. It's cheaper and denser and slower than SRAM. DRAM has traditionally been the choice for off-chip main memory. Next, we have hard disks. A magnetic disk provides very high bit density and very low cost per bit with relatively slow access times, and it is traditionally the choice for external storage. Storage is part of a memory hierarchy. Into the mix, as we have seen, as have been added, is flash memory. Flash memory has the advantage over traditional memory that is non-volatile. NOR flash is best suited to storing programs and static application data in embedded systems, while NAND flash has characteristics immediate between DRAM and hard disks. So now we're seeing, moving down the pyramid, over time, each of these technologies has seen improvements in scaling, higher bit density, higher speed, lower power consumption, and lower cost. However, for semiconductor memory, it is becoming increasingly difficult to continue the pace of improvements. Recently, there have been breakthroughs in development, new forms of non-volatile semiconductor memory that continue scaling beyond flash memory. The most prominent of these technologies are spin transfer torque RAM, STT RAM, phase change RAM, PC RAM, and resistive RAM, ReRAM, or sometimes called RRAM. All of these are in volume production. However, because NAND flash and to some extent NOR flash are still dominating the applications, these emerging memories have been used in specific specialty application, have not yet fulfilled their original promise to become dominating mainstream high density non-volatile memories. This is likely to change in the near future. So in this figure where we're showing this, and we talked about a few things that aren't listed on that table, just to give you some greater perspective of that. Well, let's talk about some of these non-volatile RAM technologies that were just very briefly mentioned on the last chart, and then we'll be finishing up this chapter. So STT RAM is a new type of magnetic RAM, MRAM, which features non-volatility, fast reading speeds less than 10 nanoseconds, and high programming endurance greater than 10 to the 15 cycles, and 0 standby power. The storage capacity or programmability of MRAM arises from magnetic tunneling junctions, MTJ, in which a thin tunneling dielectric is sandwiched between two ferromagnetic layers. So we're giving you a little introduction and getting into the physics, into the microelectronics and device physics. And so you can be thinking about this, and maybe this, for some of you, it might be an area of interest. So this storage capacity and programming of MRAM arises from the magnetic tunneling junction, MTJ, in which the thin tunneling dielectric is sandwiched between two ferromagnetic layers, as I said. One ferromagnetic layer, pinned or reference layer, is designed to have its magnetation pinned, while the magnetation of the other layer, that is the free layer, can be flipped by a right event. An MTJ has a low, that is high resistance if the magnetation of the free layer and the pin layer are parallel. That is, so you can either have low, or you can be thinking, I'll just go with these terms, has a low resistance if the magnetation of the free layer and the pin layer are parallel. In first generation MRAM designs, the magnetation of the free layer is changed by the current induced magnet field. In the STT RAM, a new right mechanism called polarization current induced magnetations, switching is introduced. For STT-RAM, the magnetation of the free layer is flipped by the electrical current directly because of the current required to switch an MTJ resistance state is proportional to the MTJ cell area. STT-RAM is believed to have a better scaling property than the first generation MRAM. Figure 621A illustrates the general configuration. STT-RAM is a good candidate for either cache or main memory. Next, we have PC RAM. Phase change RAM is a most mature of the new technologies with an extensive technical literature tail to it. PC RAM technology is based on the charlogenic alloy material, which is similar to those commonly used in optical storage media, compact disc and digital versatile disc. The data storage capability is achieved from the resistance difference between an amorphous, that is high resistance, and a crystalline, that is low resistance phase of the charcogenide-based material. In SET operation, the phase change material is crystallized by applying an electrical pulse that heats a significant portion of the cell above its crystallization temperature. In reset operation, a larger electrical current is applied and then abruptly cut off in order to melt and then quench the material, leaving it in an amorphous state. So figure 621B illustrates the general configuration. PC RAM is a good candidate replacement or supplement for DRAM for main memory. Finally, RERAM, also known as RRAM, works by creating resistance rather than directly storing charge. An electric current is applied to a material, changing the resistance of that material. The resistance state can then be measured, and a 1 or a 0 is read as the result. Much of the work done on RERAM to date has focused on finding appropriate materials and measuring the resistance states of the cells. RERAM designs are low voltage, endurance is far superior to flash memory, and the cells are much smaller, that is, at least in theory. Figure 6.21c shows the RERAM configuration. RERAM is a good candidate to replace or supplement both secondary storage and main memory. Well, that finishes up what we've covered. And so just to review, a lot of details of internal memory that we've talked about. We've talked about the organization of memory. We talked about DRAM, dynamic RAM, SRAM, static RAM. We talked about read-only memory. We talked about the different types of chip logic and packaging, and other types of things, including interleaved memory approaches. We talked about error correcting, and so this is commonly used in memory, say on the order of about 10% overhead is used for taking care of that, like a Hamming code or a sec-dead approach is something that we talked about. For EDRAM, we looked at both the IBM and the Intel configurations, and so this is getting a sweet spot for caching structures. And we saw how that was used for caching and pseudo caching. We saw this dual data rate DRAM, so DDR DRAM, and we also saw for in that area the synchronous DRAM and also different levels of DDR 1, 2, 3, and 4. We talked about flash memory, and so for this we were talking about internal memory. The next chapter we'll talk about it for external applications, and there's two implementations, either a NOR or a NAND. NOR is typically used for embedded systems, and then we very briefly in the last couple of charts talked about some newer non-volatile solid-state memory technologies that are looking very promising. All right, thank you very much. That'll finish our lecture for now.